For years, our universe and how it came to be was really a mystery. Theologians and philosophers have filled in the gaps over the centuries, but recent developments in science may give us a clearer understanding on the past, present, and future of the universe. Here now to tell us more about these developments, Lawrence Krauss, theoretical physicist and the author of A Universe from Nothing: Why There Is Something Rather Than Nothing. That's a great title.
I thought so.
Welcome back to TVO.
It's nice to be back.
Remind people, you were with us a number of years ago at we did a program in Waterloo.
Yes.
At the
space,
PI.
Space exploration.
Right, at the Perimeter Institute. And how are your arms today?
Well, actually, they're pretty tired. I just came in from Australia, so.
I'm a good straight man, eh? I'm just going to set you up all day long. Yeah, so thank you for making the long schlep from Australia to here today. We're really grateful to have you in. I want to know just off the top, when you first published this book, you've got the paperback out now, but when you first published A Universe from Nothing, what sort of reaction did you get?
Well, I was actually surprised at the strength of the reaction. The idea, people were, for me, the idea was to explain the remarkable discoveries in cosmology about the universe in the last 30, 40 years that tell us we might have come from nothing. But the reaction to this, to saying that we've sort of potentially answering this age-old question, why is there something rather than nothing, was really strong. People were offended. Because after all, for many people, it's kind of the last bastion of God. And if science infringes on that area, it's very terrifying. And I was surprised, not just from theologians, but from philosophers in particular, that this philosophical question of can something come from nothing, the fact that we kind of move the ground underneath their feet really offended some people.
And you were surprised by that offense?
Yeah, I was.
You shouldn't be offended.
Well, I wasn't surprised by the theological offense because I was attempting to offend, but the philosophical one surprised me more.
So why'd you write the book?
Well, I wrote it because our picture of the universe has changed amazingly. I mean, these are some of the most amazing ideas and discoveries in human history, and they confront common sense. But they also give us a new sense of where we come from, which is really what science is all about, and really the questions people ask. I mean, for me, the value of science is sort of cultural. It changes the way we think about our place in the cosmos. It's not just the technology, it's the ideas, like art, music, and literature. And what more profound idea than whether we could have come from nothing? And the fact that the universe, what we've discovered is that the universe looks like a universe that could have come from nothing. Does that mean it did? Not, it doesn't guarantee it. But the fact that that's the case, the fact that that's even plausible, is worth celebrating.
You want to just explain what that means, that it looks like it could have come from nothing?
Well, you know, we live in a universe of 400 billion galaxies, each containing 100 billion stars. There's a lot of stuff out there. And all common sense tells us that all that stuff couldn't come from nothing without some supernatural shenanigans. It seems to violate the laws of physics. But what we've discovered is that, in fact, it's possible. In fact, the total energy of the universe could be zero, which is a first clue that maybe it could come from nothing. That when you, in physics, there's once you include gravity, there's positive energy and negative energy, and our universe appears as if its total energy could be precisely zero, which is the first hint that maybe it could come from nothing. That and the great discovery, which is one of the real reasons I wrote the book, this discovery that nothing is much more complicated than we thought, that namely empty space. You take a region of space, get rid of all the particles and all the radiation, and so there's nothing there. That empty space weighs something, and we don't understand why. And so that wonderful mystery is worth talking about.
Okay, this is going to be the first time of many times over the next 2 days that I say to you, I don't understand. I need you to help me on this. Okay. Energy is zero. I look all around. There's lots of energy everywhere. How can you say that the energy of the universe is zero?
Well, let me take you back to one of your favorite times, high school physics, okay? So I throw a coin up in the air, it comes back down. I throw it up faster, goes a little higher, comes back down. If I throw up really fast, it doesn't come back down at all, as long as we forget the roof and all the rest of the stuff. Well, we teach high school students one way to calculate that. We turn it into accounting. It turns out the energy of the coin has a positive piece, we call it the kinetic energy, and a negative piece, which is the potential energy due to gravity. It's actually negative. And we add those two pieces up, and if you make the positive piece big enough, so the total energy is positive, it'll escape without coming back down. If the total energy is exactly zero, where the positive energy from the speed is equal to the negative energy from gravity, then it'll just escape. It'll go up, slow down, and never quite stopping. So you see, gravity has this negative piece. And if you can balance the two, the total energy can be zero. And in fact, what's amazing is it turns out, one of the things we've measured with in fact, one of the other great discoveries in the last 20 years is we've measured the geometry of the universe. Einstein told us that space is curved in the presence of matter. And one of the big questions of cosmology, the 20th century, in fact, was what's the curvature of the universe? Is it so-called open, closed, or flat? Flat being the boundary between a universe that closes on itself and one that's open. And it turns out that we've discovered the universe is flat, as we theorists knew for reasons we may talk about in a bit.
The Earth is not, but the universe is.
The universe is flat in a three-dimensional sense. It's not flat like a pancake. It's flat like it's the universe you always thought you lived in, where the x, y, and z axes are perpendicular and remain perpendicular. Well, what's amazing is it turns out in a flat universe, the energies add up to be precisely zero. The energy of every galaxy, all the galaxies are moving away from us. Hubble discovered that in 1929. Everywhere we look, all the galaxies on average are moving away from us. If you measure their speeds and then you work out the attraction, the two add up to precisely zero. An amazing discovery that confirms this notion that not only is the universe flat and mathematically beautiful, but begins to give this inkling that maybe we could come from nothing.
Okay, but let the record show you're talking physics, not English here.
Absolutely. Physics, not English. Well, I try to make the two balance the two.
You know what I'm saying? You're talking physics, not reality. In reality, there's lots of energy here, but in physics...
Well, no, I'm talking reality. Physics is reality. But, when we look on Earth, yeah, there's lots of energy, and it's a really weird concept. Mm-hmm. And throughout our discussion, I suspect, we may violate common sense. And the point is, why should the universe obey our common sense? We evolved on the savannah to avoid lions, and we didn't evolve to understand quantum mechanics. And so one of the great things about science is it forces us to refine our idea of what's common sense. It forces us to have our beliefs conform to the evidence of reality rather than the other way around. The universe may not be like we'd like it to be, but it doesn't really care.
Why is defining nothing considered so controversial in your business?
I don't think it's so controversial in my business. I think, well, look, because we've changed the notions. I mean, well, actually, we've begun to define the notions. What is nothing? Well, I think the idea of nothing is the absence of something, right? Mm-hmm. But that makes nothing a physical quantity, not a philosophical one, because if something's physical, then the absence of something is physical. And as I say, when you think about that, well, what's the absence of something? The simplest version of nothing, it might be empty space, just the nothing of the Bible, an infinite, dark, empty void. But as I have been mentioning, that empty space is actually quite complicated. When we put together quantum mechanics and relativity, two of the foundations of 20th century physics, we put them together and we find out that empty space is actually a boiling, bubbling brew of virtual particles popping in and out of existence every second. So quickly you can't see them. In fact, if you try to measure them, they're not there. But they have an impact that we can actually calculate and predict. And in fact, it produces the best predictions in all of physics. It explains why the atoms in your body behave the way they do, and in fact, why your body has mass. So we know that prediction is true, even though we can't measure those things exactly. But that changes the ground rules. It says that empty space is really complicated. Now, some people say, well, if there's virtual particles there, it's really not nothing. But there are no real particles. You try and measure things there, there's nothing. But those virtual particles can give space energy. And in fact, we've discovered, to our great surprise, it won the Nobel Prize 2 years ago, that empty space has energy. And if you put energy in empty space, then it's really strange, because it's not like the normal energy of you and I. It's not gravitationally attractive. It's actually repulsive. And we've discovered the expansion of the universe is not slowing down like any sensible universe should do. It's actually speeding up. It's getting faster and faster. And that's because it's dominated by the energy of empty space. But it actually gets a little more interesting, because you might say, well, look, that's not nothing, because there's still space. And I say, okay, but it turns out when you apply quantum mechanics to gravity, then even space itself can pop into existence from nothing. Space and time can spontaneously pop into existence. Whole universes can pop into existence. And most of them will disappear at a timescale so short you wouldn't know about it. The ones that can survive for a long time have zero total energy. And so you're beginning to see the thread here. And then it goes to another stage, which we may get to, where it turns out you may say, okay, well, look, you got no space, no time, no particles, no radiation. That's a pretty good approximation, nothing. But there's still the laws. Who created the laws? And what we've discovered as we think about these things in the last 10 years or so, and again, this is speculative, but it's based on everything we know of in particle physics right now. It's quite reasonable to suspect that even the laws themselves came into existence when our universe came to existence. There could be many different universes, and each one of them, the laws of physics are different. They spontaneously arise when the universe arises. So you got no laws, no space, no time, no particles, no radiation. To me, that's nothing.
All right, let me follow up with, I thought, the first big surprise for me in the book, which was, I always thought that physics, and certainly my business, is all about the why. And you tell us quite early on in the book, you're actually not really into the why, you're into the how.
Yeah, sure. Do you have kids?
Explain the diff. Yeah.
Okay. You ultimately know the only answer to the why question
is
because go to bed.
That's right. Why?
Because ultimately, why presumes purpose, if you think about it. It presumes purpose, but what if there isn't purpose? Whenever we say why, we really mean how. We say, let me give an example, which I used in the preface of the paperback version because people were asking me this question. So Kepler, there used to be 6 planets, okay? And Kepler had a great explanation for why there are 6 planets. Namely, there's purpose.
Hundreds of years ago, right?
Hundreds of years ago, because God intended it to be that way, because there are 5 platonic solids, beautiful platonic solids based of these regular polyhedra. And he said, oh, look, you can fit the 5 platonic solids, and you can fit the orbits of the 6 planets, each of them outside a platonic solid. And there's a beautiful mathematical reason why God, the mathematician, would create this universe. So that was a why answer to the question. But of course, it was completely wrong. There aren't 6 planets. There are 9 planets. To me, there are always going to be 9 planets. Pluto will always be a planet.
You're always going to count Pluto.
Yeah, my daughter did her 4th grade project on Pluto, and I'm not going to give it up so easily. But the point is, we know there are lots of solar systems now and around lots of stars, and what we really care about is not why are there 9 planets, but how are there 9 planets? Is our solar system unique, or are there lots of solar systems with many planets? And how did are they all have rocky planets on the inside and gas planets on the outside? We want to understand our origins. So the real question is, how are there 9 planets? This question, why were there 6 planets, is really irrelevant. And so when you think about it, whenever we say why, what we really want to understand is how things came to be. And if you insist on why, then you're insisting on purpose. But everything we know about the universe, when you look out, tells us there's no evidence of purpose. Now, I want to be, before you get lots of mail, I want to indicate that doesn't mean there's no purpose. Maybe there is some purpose. There's just no evidence that there's any purpose.
You haven't figured it out yet.
No, it's not that. There's no evidence. The universe behaves just like a universe that had no purpose. Now, to me, a universe that behaves as if it has no purpose and one with no purpose are effectively the same thing. So God is redundant. But we can get into that if you want.
Yes, don't get ahead of me yet. Okay, you show me a Kepler, I'm going to raise you and bring you a Doppler.
Okay.
What's the Doppler effect?
Well, the Doppler effect, there's a cartoon I like to show. It has these 2 cowboys on the plane looking at this train, and one says, I love hearing the lonesome wail of the train whistle as the magnitude of the frequency changes due to the Doppler effect. But the Doppler effect is this famous example. If you hear an ambulance in Toronto, when a car, an ambulance, or a train is coming towards you, the whistle sounds higher. When it's moving away, it sounds lower. That's because sound is a wave, and in front of the train, the waves get compressed, and that means their wavelength gets smaller, their frequency increases, they get stretched out behind the train. It turns out, for very different reasons, the same thing happens to light. So we look at stars, and one of the great discoveries of the 18th, or actually almost 17th, but 18th century and then the 19th century, was that star stuff is the same stuff as Earth stuff. We look at the light emitted by stars, and it's the same set of colors that's emitted by hydrogen gas here in the laboratory, telling us that stars are made of hydrogen. In fact, helium was actually first discovered in the sun before it was discovered here on Earth by looking at that spectra. So we know stars are made of the same stuff, but if the stars are moving away from us, all those frequencies of light get stretched out by this effect called the Doppler effect. And it tells us that we can measure the speed of stars, and in fact, stars and galaxies,
and the universe,
universe as a whole, because if we measure the galaxies moving, if we can see bright enough stars, we can look out and see the whole expansion of the universe. That's what, in fact, Hubble discovered in 1929, is that these galaxies, and by the way, this is really interesting to point out, In 1925, when Hubble first started doing his stuff, the universe consisted of one galaxy, a single galaxy, our own, surrounded by an infinite empty space. That's a human lifetime ago. That's 83 years ago or so. So it's amazing to think that in a single human lifetime, we now know there are 400 billion galaxies. We're like the early map makers. We're just beginning to understand the universe on larger scales, which is not, therefore, surprising that we're surprised all the time, because we keep understanding the universe on larger scales, and it's more amazing than we imagine.
Doesn't it drive you nuts that you're not going to be around in 100 years to know exponentially so much more than you know now?
Yeah, of course it does, but on the other hand, it's an exciting time to live in. It's an amazing time. Our picture has changed completely of the universe. So I'll live with that and I'll be happy with the surprises I'm getting every day.
It's a fraction of what they're going to. Whoever you are 100 years from now, what you know is a fraction of what he or she's going to know.
But I'm happy that what I know is a lot greater than what was known 100 years before.
What an optimist.
Yeah. Well, you know, although my friend Cormac McCarthy says I'm a pessimist, but that's no reason to be gloomy.
Let's bring up control room if we can. Middle of page 2 here, the image of the standard candle. And there it is. Okay. To measure distance, you use what you call a standard candle. What is that?
Okay, look, you know, we want to measure distances in the universe to see how the universe is expanding, to frame the universe. But we don't have tape measures that are long enough to get the distances between stars are amazing. The distance between us and the nearest star is 4 light years. It takes light 4 years to get to the nearest star. The distance across the Milky Way galaxy is 100,000 light years. And the distance between even the nearest galaxies in our own are millions of light years. So clearly, we have to figure out how can we measure distances. And we use physics, of course. And one of the ways to measure distance, I could measure distance in the studio. It wouldn't be good TV, but if I turned out all the lights but one in the back of the studio, and you and I are both old enough to remember light meters on cameras, okay, if I knew that was a 100-watt light bulb, and I had a camera here, and I looked and I saw there was 1 watt of light coming into the camera, and I know light spreads out a certain way, I could work out how far away that light is, okay? So if the universe were populated by 100-watt light bulbs, we'd be fine. But it's not. So we look for what's called a standard candle, something whose intrinsic brightness we believe, for many reasons, we understand. And then we look at, say, a distant galaxy and say, how bright is that object? How bright does it appear in that galaxy? And then we work backwards and we figure out how far away the galaxy is. And that's the hard part. That's why Hubble got the answer wrong in 1929. And what's really amazing is that we found what we think is a really good standard candle. In that image you showed, it was a bright spot. And it was as bright as the center of a whole galaxy, which contains 10 billion stars. It was a star that just exploded, the brightest fireworks in the universe, a supernova explosion. And when stars explode, they shine briefly with the brightness of 10 billion stars. And that object out there, which looks like it might be a star in our galaxy, is actually a star in that galaxy that's just exploded. A very particular type of exploding star called a type 1a supernova. And for reasons that we probably don't need to go into here, it turns out that that's a wonderful standard candle that observers have been able to use to peer out, because supernovae are so bright you can see them across the universe. We can now measure distances across the universe. Now, what is equally amazing to me is that supernovae occur very rarely. It's fortunate for us that stars don't explode more often, perhaps, but it's fortunate for us that they explode. Stars explode about once per 100 years per galaxy. So how can you study these things if it's once per 100 years per galaxy? I often say, well, you can assign a graduate student to each galaxy. 100 years is about the right time for a PhD. If graduate students die, well, they're cheap. You can get new ones. But we don't need to do that because the universe is big and old. And so rare events happen all the time. If you went out tonight outside of Toronto in a place where you could actually see the stars and held up a sort of a hole in your hand, a dime-sized hole, and looked out in a region of the sky where there were no stars, with one of our biggest telescopes on Earth today, in that region you could see 100,000 galaxies. And if you work it out once per 100 years per galaxies, on a given night you're going to see a few stars explode. And observers do. They apply for telescope time. They say, tonight we're going to see a few stars explode. And they might see one, they might see two. It might be cloudy. But that's how we can study these objects. And those objects have been used to measure distances and therefore from their spectra also the speeds of the galaxies they're in, and allows us to map the expansion of the universe and discover that it's speeding up. It was that measurement of those supernovae and the speeding up of the universe that won the Nobel Prize.
I can see why it would be important to know distance in the way you've just described it. But you also want to know the weight of the universe, and I'm a little murkier on why that's important to know.
Well, because, in fact, Einstein tells us that space is curved in the presence of matter. And what we want to know is the curvature of space. Just like, for example, if we want to know how fast you have to send something up, Canada, I know recently sent up a satellite the other day, and if you want to know how fast you have to send something up to escape the Earth, you also need to know the mass of the Earth. Mm-hmm. And similarly, if we want to determine the future of the universe, and which depends on its geometry, you want to weigh the universe. You want to know what the total mass of the universe is to know if those speeds are fast enough to keep things going. I mean, the reason I got into cosmology as a particle physicist is I wanted to be the first one to know how the universe would end. It seemed like a good idea at the time. And if we know the speeds, well, we got to know the mass, because then we'll know if the speeds are fast enough to keep things expanding out. Now, it turns out all that's changed due to the energy of empty space, but we want to weigh the universe to determine the geometry of the universe. And I actually would have thought when I was a graduate student that we'd never get there in my lifetime. So I don't have to wait for those people 100 years from now. What's amazing is we have weighed the universe.
And?
And the answer was wrong. What we discovered we can weigh systems of galaxies. The largest bound objects in the universe are called clusters of galaxies. They're maybe 10 million light years across. If we can weigh them, since anything that can fall into anything will fall into a cluster, then we can weigh the universe. And we weigh them using gravity, because Einstein told us that mass curves space. And we can actually use those large clusters as lenses. If there's a light source behind a cluster, the light from it can come around and be lensed, just like my glasses magnify things. And we've actually measured this gravitational lensing phenomena, which Einstein, by the way, said it would never be observable, but he underestimated observers. And we've weighed these systems, and we found that there's only 30% of the mass needed to make a flat universe. And that was a big problem, because as I say, theorists like me knew the universe was flat because it's the only mathematically beautiful universe. And we were therefore sure the universe was flat. But here these observers kept coming up with only 30% of the stuff needed to make it flat. But then what we've discovered, and we can talk about that observation, is that the universe actually is flat. And the rest of the 70% of the energy in a flat universe comes from the energy of nothing.
Back again, full circle here.
Okay.
Two more things. We've got about 5 minutes to go, and I want to touch on two more things. You physicists have a habit of wanting to put a Greek letter on so many things.
Yeah, it makes us sound scholarly.
Is that why you do it?
I think so.
Okay, so
I don't know.
what's omega?
Omega was the holy grail of physics in the 20th century. What omega is basically represents a number that represents the ratio of the actual density of the matter in the universe divided by the density of a flat universe. So if omega is less than 1, the density is less than a flat universe. That makes it open. If omega is greater than 1, more. It's closed. And what we discovered when we weighed galaxies was omega was 0.3. 30% of the energy needed to make a flat universe. That's what caused people like me headaches, because we wanted omega to be 1. Mm-hmm. And by the way, if omega is 1, then the total energy, gravitational energy of the universe is 0. That's another reason why it's so beautiful. And here we were getting a factor of 3 less than we imagined. And of course, there's a loophole if you weigh galaxies and clusters, because you're weighing the total amount of energy around galaxies. What if there's energy where galaxies aren't? What is where galaxies aren't? Nothing.
I can't cope.
It's hard, but
dropped
we'll get
something.
there.
In your penultimate answer, you dropped a little something, and I should follow that up in our remaining moments here, which is you started by trying to explore how it all ends. How far have you got in that exploration?
Well, of course, the nice answer is it's kind of like Charles Dickens' Christmas Story. I can tell you what the end might be, but I can't tell you for sure what it will be, because we don't know the nature of the energy in empty space. We don't know what's causing it. But if it remains constant, which is the best guess, then the future is miserable. That's what I can tell you. So much for the far future. Because what will happen is the galaxies we now see will be moving away from us faster and faster and faster. And in the far future, they'll actually be moving away from us faster than the speed of light. It's allowed in general relativity. And the rest of the universe will disappear in a mere 2 trillion years, which may not seem like a long time, or maybe compared to this interview, it won't seem like a long time. But in 2 trillion years, all the rest of the galaxies that we can now see will have disappeared. And I find that poetic, because in fact, there'll still be stars in 2 trillion years, and there'll therefore be planets that can be around those stars and life forms that can exist around those planets. And astronomers will arise ultimately, and they'll learn the laws of physics and quantum mechanics and relativity, and they'll build telescopes. And when they look out, they'll see the universe we thought we lived in 100 years ago, because they'll see a single galaxy surrounded by vast, eternal, empty space, and all evidence of the Big Bang will have disappeared. And they'll poetically come up with a picture which is the false picture we had 100 years ago.
You say poetically. It sounds kind of depressing, actually.
Well, maybe, but it's kind of nice full cycle. And therefore, in fact, it's not depressing, because you talked about being depressed about observers 100 years from now. We can be excited that we're living in this time in the universe. We can see what we can see. In the far future, it'll be much worse. So there's reason to live, Steve.
Always, Lawrence, always. Well, if only because we need to hear the second half of this interview, which will be coming up tomorrow night. And I want to thank you for setting the table for tonight. And we want to remind everybody that Lawrence Krauss will be with us again tomorrow night, and we hope you can join us for that, too.
Support Ontario's public television. Donate at TVO.org.